So, good day students, and welcome to a new nugget on how biomass can be used for energy. In the previous nugget, we talked about the use of biomass in large-scale CHP and CHPC plants, but not all bioenergy is used in a large scale. Already since ancient times, has biomass been used for cooking and heating in individual houses and dwellings. Today, more and more single-farm plants are erected, and more small-scale plants for heating and for combined heat and power production are installed at local industries. Such installations may play a major role for survival in emergencies like major power failures, but are also becoming more and more important for the local power grids. So let's talk a little about how these plants are designed and which technologies and which types of biomass are the most suitable. With small scale, we mean plants with thermal power to 1 or at the very most some 5 to 10 megawatts. But basically, there is no lower limit. In the small scale, like with a household or a farm or a small hospital or so, you will for economic reasons want to get as much electricity as possible. To get that, you will want to maximize the Carnot efficiency. But like any CHP application, is the cooling temperature, limited downwards, since you want to have the heat delivered at a useful temperature. The cooling temperature must then be higher than the temperature at which you want to have the hot water. So you want to have as high a starting temperature as possible. Also, you do not want to handle superheated steam in the small scale, because superheated steam is very dangerous. Internal combustion engines will give a very high initial, that is hot, temperature when burning in the cylinder, and the cooling water will typically be about 80 degrees C. So that is most often the preferred technique to be used in the small scale. Let us now distinguish between two completely different situations. The first case is that the biomass lends itself best for digestion. This is a common case on cattle or chicken farms, in which case the biomass, the droppings, is produced more or less continuously over the year. And then there is the case that the biomass lends itself best for thermochemical processes. This is the common situation in some farms where straw may be available on a seasonal basis, or in wood-based industries where sawdust, cutter shavings and cut-offs may be available on a continuous or discontinuous basis. The main difference between these two types of biomass is that while the droppings, the digestible droppings, will not be suitable for storage since they will digest already during the storage, can the lignocellulose and the straw be stored for some time and used at will at a later instance. Both situations can well supply a local, combined heat and power system. The droppings from a cattle or chicken farm can be digested to produce biogas in a local farm-scale anaerobic digester. And the biogas can then be used in an internal combustion engine. The engine can run a generator, and the cooling water from the engine can be used for heating. With anaerobic digestion is the gas production a more or less continuous process. And since you will not want to store the huge annual amounts of gas, this means that these systems will be designed for a continuous operation. The same type of a setup, an internal combustion engine, can also be used in combination with a small gasifier. The gasifier can use straw as a feedstock, but then the fuel gas from the gasifier will be corrosive because of the chlorine content in the straw. So there may be a need for at least some simple type of gas cleaning. With lignocellulose, such as wood residues, is the corrosion problem less pronounced, since the contents of chlorine and sulfur is much less in lignocellulose. In these cases, since the fuel is non-digestible, can the system be designed for intermittent use. So the gasifier may be turned on and off, and the system may act like a spare or like an emergency generator for sudden power failures. In the case of a gasifier, generally the gas quality and the content of heavy hydrocarbons, water and/or corrosive components may be the most crucial factor. Just imagine, for example, that the gas intake to the engine becomes blocked by condensing tar. Or imagine that the throttle valve corrodes. It must also be said that internal combustion engines are by no means the only option in the small scale. Micro gas turbines as well as solid oxide fuel cells may also be used. But the internal combustion engine is the most common, so that is what we put focus on here and now. A local or individual CHP system is a significant investment for the individual farmer, so it must be economically viable. To promote installation of this type of systems, have different countries introduced different types of support systems. One of the countries where the farm-scale installations of digesters has been most successful is Germany. So read the paper by Daniel Gronke. Only a limited number of countries are members of the International Energy Agency Task 37, which is the one for biogas. But it may be interesting for you to find statistics for your own country and also to look in the summary report and do a comparison of how the financial support systems in the different countries have been organized. Finally, it is very important not only to achieve a high total efficiency, but also to maintain the energy performance at its best. So this is a purely technical aspect on the system. A very good background description for this is found in the paper by Klaus von Mitzlaff. You will find that paper if you first go to the biogas homepage at the University of Florida and then search for the word engine. For systems making use of non-digestible biomass, such as straw or wood residues or alike, is thermal gasification the main option. Again, just like with biogas, will the gas quality have a pronounced influence on the engine performance. It is no big problem to take the quality aspects for the engine into account using the general theory presented by von Mitzlaff. A slightly old, but not outdated, paper from the Italian Engineering Association for Thermal Machines in 2014 is available from Science Direct. This paper presents a comprehensive overview of the properties of the product gas as a function of the system solutions and techniques. The paper also briefly mentions other generating options than the internal combustion engine. And you may also want to look at the country-specific reports about gasification from the International Energy Agency. There are also lots of case studies and examples of new designs and solutions available on the web. But the references given here aim to give you the general background to the techniques. And you will also find very short information about the techniques in the BusyPlan Handbook column 4. But the papers I referred you to here are much more comprehensive, and they aim to give you a first insight into the techniques. The two YouTube films on this slide are to show you that not only house heating and electricity may be produced, but that small-scale plants may play many roles and help to solve many problems. So when looking at these films, you should also listen to what benefits are gained beside the locally produced heat and electricity.